So now we've seen that in the normal equations, this matrix S equals A transpose A that we get is a symmetric matrix, regardless of what A is, even though A is rectangular. And that means, remember, that S is equal to LDL transpose. We have this factorization, which is really just a special form of the LU factorization, with no pivoting. So if we turn off pivoting in the LU factorization, we can do this. And we know that pivoting is sometimes necessary, so we're going to have to justify that if we want to use that. And the way we do it is another property of matrices that we call positive definiteness. Now this one definitely looks a little bit weird, so I'm going to give you the punchline first, which is that positive definite matrices act an awful lot like positive numbers in the real scalar case. And the most important thing that we know about positive numbers maybe is that they have square roots. And something similar happens for positive definite matrices. So if we look at this S, where it comes from is A transpose A, if we look at this special form here, okay, so X has to be an n vector. Remember, S is n by n. So what we have here is 1 by n times n by n times n by 1. That's what's inside this little circle here. And so that's going to be a scalar. Just a number. And this special way of doing X transpose matrix X has a name. It's called a quadratic form. Okay, quadratic because X appears twice as the product in this product. Okay, so we put in what S is, and now we have X transpose AX. Okay, and then in the next step, I use the fact that this is a product of transposes. So if we reverse the order, it's the transpose of the product. And now we recognize that this is an inner product of the vector AX with itself. So that's equal to the 2 norms squared of that vector, AX. While the 2 norm of any vector is always greater than or equal to 0. So we've shown that this quadratic form X transpose times S times X is a non-negative number in the case of this particular form for S. Okay, now when can this quadratic form equal 0? Well, the only way that X transpose SX equals 0 is if the norm of AX is equal to 0. Right? So maybe I should write that out. So if that quadratic form is equal to 0, well, we just showed that it's equal to the square of this guy. And the only way for the 2 norm of a vector to be 0 is if the vector itself is equal to 0. Okay, when can that happen? Well, remember that A times X is a linear combination of the columns of A. If AX is equal to 0, and X is a non-zero vector, then that would mean that the columns of A are linearly dependent. This goes back to basic linear algebra. Well, in that case, if the columns of a matrix are linearly dependent, we know that its rank is not the same as sort of the number of columns, right? The dimension of the range is less than the number of columns. So, to put that another way, if we do know that this matrix A, which has n columns, if they span an n-dimensional space, in other words, if the rank of A is equal to n, then they must be independent, and the only way you can take a linear combination and get 0 is if the linear combination itself is all zeros. So what we're saying is that this is just sort of a technical condition that if the rank of A is equal to n, the number of columns of A, then we know that the only way to get a quadratic form of 0 is for the 0 vector. So we put these things together. So now we have an additional assumption about A, which is that the rank of A is equal to n. Okay, we do need to make that, but it's a technicality. All right. Given that assumption, then we know that the quadratic form is positive for every non-zero vector x. And that's the property that defines positive definiteness. Okay. So positive definiteness means that the quadratic form is positive for every non-zero vector. Okay. Here's the significance of that. Since we had that S is equal to LD L transpose, positive definiteness gives us some extra information. Sometimes we write SPD to mean symmetric positive definite. That's a common abbreviation that you'll see. So a symmetric positive definite matrix S has that the diagonal entries of D are positive. Okay, which means we can take a square root of them. So normally it wouldn't make much sense to write the square root of a matrix, but maybe you'll permit me to write the square root of a diagonal matrix whose entries are all non-negative. That's not too much to swallow, I think. And then we see that, okay, if we reverse the order, take the transpose out, a diagonal matrix is its own transpose already, so that justifies that line. And then we can see that if we call this matrix now R transpose, then this matrix must be R. And we can write that S is equal to R transpose R, where now R, because L was unit lower triangular, that means that R, which is L transpose times another matrix, is upper triangular. So this can all be stated and proved as a theorem. The details are deeper than we want to go. But given a positive definite matrix, we can write it in this form, R transpose R, where R is upper triangular. And this particular factorization has a special name. It's called a Cholesky factorization. And some extra goodies come along with it. So one of those goodies is that we can show that pivoting is never needed. In other words, you can turn pivoting off for these matrices, and it never causes any round-off problems whatsoever. So that's nice. The other thing is that essentially you have half as many unique numbers to find as in an LU factorization, right? In an L and in the LU factorization, you got to find the lower triangle of the L and the upper triangle of the U, and they have nothing to do with each other. Well, here, the two matrices are transposes of each other. They're copies of each other. This is what I was referring to as sort of the square root of S. And so therefore, since you have half as many things to find, it turns out that you can do it in about half as many operations. So as compared to 2/3 for the general LU. That's why we retain these constants in the asymptotic notation. Of course, they're both n cubed as n goes to infinity. They're both proportional to n cubed. But the Cholesky factorization at a given value of n is about twice as fast as standard LU factorization. And that's the main thing we wanted to come out of this with, is that when we solve the normal equations, we can take advantage of the Cholesky factorization and do it faster. In MATLAB, we can find the Cholesky factorization of a matrix through the command chol. Now chol is interesting. It assumes that the matrix you give it is symmetric already. It doesn't check that for you. But it does check the positive definite. It does check the positive definiteness for you. Okay, so you might be wondering, given that definition we had about quadratic forms, how do you even check whether something is positive definite? For the normal equations, we know it has to be. For another matrix, though, the Cholesky factorization process itself tells us whether the matrix is positive definite. So you get an error if S is not positive definite. Otherwise, you get the R matrix in the factorization.